Engineering Numerical Methods, Module number 7, Initial Value Problems. In engineering, we have two types of problems, initial value problem and the boundary value problem. So in the next module, we're going to talk about the boundary value problem. But for this module, let's see the difference between the two. Okay, you are given with the equation here, okay, with initial values this sort, and then you have this one for the same system, okay, for your problem, and then you have the boundary values. Now take note that for your initial value problems, you notice that the initial values are given. Okay, now initial value from the preceding system, no, meaning you have the first order, the first degree, and then this should be 0th degree and then the first degree, because your system in the second degree system. So the initial values at the the at the first y of 0 and y prime of 0 is both have values, no, while for the boundary values you are only given with a certain degree and then it is bounded, meaning you have two values, okay, that from between 0 and pi, okay, if this is x, for example, x is equal to 0 and x is equal to pi, with these two values, okay, these are considered as the boundary, and you are given with the values 1 and 2 respectively. So basically this is the boundary values, contrary to the initial value. You're just given with the initial values of the two all degrees, no, pertaining to the y double prime or the second degree variable. Okay, so basically that's the idea of our initial value problem. So basically one of the most simplest method for solving initial value problems is the Euler's method. Okay, Euler's method of solution is basically simple. It is a truncated Taylor series of y about x. So if you notice, you have the approximation here. Okay, you can look at the graph here for the y prime. Okay, so if you take the integration, this part, so this is the approximation of our Euler's method, and then the error is this one. Okay, so you can see from this math integration that from x to x plus h, you have the y prime dx. Okay, if you take that one, that will be your value, okay, f of xy from x to x plus h. Now the error will be lessened if your step value is you make h very small, and you will get your error very small also. Okay, so that's a graphical interpretation of Euler's method. Basically you have this approximation, you truncated the other higher powers of Taylor series. Okay, so we just get the first order. So this is the first degree, yeah, and then you equate to this and you will get the approximated value of your problem. Okay, so in this case integration and or derivation. So you have in the previous modules, module 6 and 5, or 5 or 6, we have discussed about the methods on differentiation and numerical integrations. So here the main difference is actually you have initial values given. Okay, so this one here. So in the previous lessons we have solved the two, okay, without these initial values. Okay, this time in module 7, most of our engineering problems we have initial value conditions. Okay, Now let's try an example to further understand this. So integrate the initial value problem. So you have this. Sorry, I think there is an error here. So this should be here. So the problem is here, y double prime minus 0.1 y prime minus x with the initial values y of 0 and then y prime of 0 equals 0. Okay, so actually this should be 1. The value here should be 1. Okay, so I think there's an error. It should be 1. Then from 0 to 2, okay, with a step value h is 0.05. So okay, very small. And we compare our solution with a numerical analytical solution, which is expressed by this one. So this is the analytical solution of this. If you solve this one using the any numerical method, analytical method, then this is one of the solution. Okay, so we will compare our numerical method with this analytical solution. So this is our code for the Euler's method. So integrate, and very simple, we just follow the idea from the top. Okay, so we just simply add, okay, individually from 0 to 2. Okay, if you look at the h is 0.05. We just actually divide 0 to 2 with 0.05 panels. Okay, similar to the previous module, and we until it reaches 2. Okay, so x stop here is a initial sorry, the final. Okay, so the final point, and then x is the arbitrary value. Okay, so and then you have the function here, our problem. So you can modify this one if you have different problem here. So you can modify this one. So but make sure that you have the f of 0. This one indicates the um, the how you so called the first order, and then this one is the second order. So you can see that this one is the y prime, okay, from this equation. Then f1 is the y double prime, and then since this one is y prime and this is y prime, so f of 0 is it's like the y prime. So y prime, y double prime. Okay, so there are two values. So basically that is how we do it in the numerical methods, like two matrix. Okay, so for the y prime on the top and then y double prime in the bottom. So we solve this one. Okay, so given any value of your x and y, you can input it in this function, so you can generate the function, okay, itself. And then okay, so start of integration. So this is the stop, as I said, from this function here. You see, it will stop at x stop. Okay, and you have the y array from 0 to 1. So initial values, 0 and 1. So these are the initial value condition. Actually, as I said, this one should be 1. And okay, we use the user defined function integrate. Given the f, we have just defined, and then x and y. So x is 0 and y is a matrix with two initial conditions, 0 and 1. Then x stop 2, and then you have h is equal to 0.25. Now this is our exact solution. We will compare our numerical method using compared with y exact, and then we plot this value here, and then we will get, okay, we can get this solution here. Okay, so we plot that one. This is our numerical method, the one in the dotted line, while the exact in the straight line. So okay, you see here the difference, no? The difference between our the numerical method and then the exact solution. Okay. Now, why? Well, how can we address this error? Okay, very simple, because it go in Euler's method we govern with h. Therefore, we can actually um, if we have the step value into 0.025, we can see that same code here, just changing this one step size, and you will see that the numerical method and the exact solution is getting closer. Okay, or you can say it, you can say that the truncation error is also half. Okay, mathematically it's actually half. Okay, so because uh, from the graph, no? So if you have this one from 0.05, let's say this is the distance here is 0.05, then 0.25, you can say that the truncation error is also half. Okay, so that's it. And so you see the difference. Now, in our next method, actually part of module 7, we will talk about Runge-Kutta method, because Euler's method is actually not so efficient, because um, as we as we go with higher order differential equation or integration, it will be computationally expensive also. Okay, so for your challenges, you can try solving these questions here. You can try solving also the differential equation on the number 3. Okay, so that's it. The engineering numerical methods. Thank you.